We all know what numbers are. 1, 5, 20,934. But did you know that there are numbers that exist, but we can't represent using, well, numbers? Well, I'm going to show you how to prove this. But wait, I'm sure you're thinking, I haven't come across any of those numbers, so what do I care about them? Well, my first response would be that this would make much better conversation than talking about, say, the weather. But on a more serious note than that, regularly using your brain is a fantastic way to ward off Alzheimer's. And speaking of the brain, that is going to be the number one thing on the list of necessary items. It would also be helpful to have some paper and a writing utensil. The fourth item needed is a set of real numbers. Defining that fourth item is where we start off in step 1. This is kind of a big step, so how about 1A? Define the range of the set. For this proof, we are using real numbers from 0 to 1, but not including 0 or 1. So a half, a third, 0.1415926, da 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 da. Step 1B is defining what we intuitively know as those real numbers. We're going to make what's known as a finite state diagram. I like to think of this as a board game, where your goal is to make it to the end space using each character or digit of your number in order. So let's consider the decimal format of 0.034. We're starting off here. The only valid character for any number within our range is the decimal. That moves us to this space. Now, from here, any digit from 0 to 9 is acceptable. However, this isn't quite enough. We require at least one non-zero digit to give this decimal a value greater than 0. So we can move to this third space using any digit from 1 to 9. And again, we can circle back on this space using any digit 0 to 9. That third space is an ending space, so we're going to put another circle inside of it. So if we consider 0.034, we move from the first to the second space using the decimal. We use up the 0, looping back around to the second space. The 3 moves us to the third space, and the 4 loops us back around on that third space. We've ended on the ending space, so this is a valid real number. Step 1C is to determine equality within these numbers. Now, why do we do this? So that we can make these numbers infinitely long. 0.034 is equal to 0.0340 and 0.03400000000 and so on. So trailing zeros do not change the value of the number. We can represent this by adding a fourth ending space that requires a 0 to get to and only loops on a 0. Any number that ends on that space is equivalent to the number that you had so far used up on the third space. So if we consider 0.0340, we know that we can get to the third space using 0.034. We can use up that last 0 to move to the fourth space, and since we are ending on that space, it means it's equivalent to 0.034. If we have 0.03401 and start at the third space again, if we move to the fourth space using the 0, we have nowhere to go using the 1, so it's invalid and therefore not equal to 0.034. We now have our set of real numbers, so now for step 2, we need to make an infinite length list of infinite length real numbers. Well, we can't really do that, so let's list maybe the first 5 digits of the first 5 numbers we come up with. Let's start with 0.5. Now we would normally have only that one digit there, but we need these to be infinite length decimals, so we're just going to tag zeros on the right forever and ever. We can also have a third, so 0.3333333 and so on. The decimal portion of pi, perhaps, so 0.1415926. Maybe a pattern of 1, 2, 3, 1, 2, 3, 1, 2, 3 that repeats forever. Or perhaps just some random numbers like 0.642279 something or another. Because this is an infinite length list, it's going to contain every single number out there. These are just 5 that we picked. Step 3 is to create our numberless number. To do this, we put together the first digit of the first number, the second digit of the second number, the third of the third, and so on. This gives you an infinite length number that includes one number from every single number that exists. In our case, the number starts with 0.53117. Now we increment every digit on its own. That means that 0 becomes 1, 1 becomes 2, 2, 3, on and on up until 9 wraparounds to 0. Note that there is no carry here, so the increment of 9 does not become 10. This turns our number into 0.64228. You might note that this number is almost identical to our fifth number, except for its fifth digit. Because of the process of incrementing each digit on its own, this number is now guaranteed to be different than every nth number in the list at its nth digit in that number. Well, why does that matter? The thing is that this infinite list already contained every number out there. However, we just made a number that cannot be on the list. You might say just stick that number in the last spot on the list and voila! The list now contains every number. But then, if you do this process again, you will get a number that disagrees with that number you previously found. So, what exactly is this number? I don't know. No one does. That's the point of it being unrepresentable with our current notation for numbers. I can tell you what the first 5 digits are, according to this proof, but if you used different numbers than me, you would get a different non-existing number. The key here is that this is an infinite by infinite square. And so it doesn't matter how many new rows you add to it. It's always infinite by infinite. So you can always draw a diagonal through each and every number. Now that you know how to prove that there are numbers that can't be represented by numbers my way, try seeing if you can do it with whole numbers on a range of 0 to infinity. Or is it necessary for the digits to be incremented? Could there be some other relationship that would also work? What is required by that relation for it to work? Get out there and use those brains.